Hi everyone, my name is Yihui. I'm a PhD student at Stanford University, where I am now, and I'm delighted to be here at a virtual TQC to share about our work entitled Private Learning Implies Quantum Stability. This work was done in collaboration with my wonderful collaborators Srinivasan Arunachalam and John Smolin, who are both at IBM. So the results that I'm presenting today will be a snapshot of those in this paper, which we uploaded onto the archive in February this year. This is a talk about reduced quantum learning models. And as with all such talks, we have to start off with an observation, which is that full quantum state tomography, ubiquitous and important as it may be in quantum experiments, is a task that consumes lots of samples. And just to be clear with the definitions, full quantum state tomography refers to the task of, given copies of an unknown d-dimensional quantum state rho, return an estimate of the full density matrix of rho. And when we say lots of samples, a couple of years ago, two breakthrough papers proved that the number of samples that are necessary and sufficient to accomplish this task is the square of the dimension of the quantum state. This is of course bad because d is exponential in the number of qubits that the quantum state is on. So if you want to estimate the full density matrix of the quantum state, you got to prepare exponential number of qubits, number of copies of that state. So a couple of years ago, Scott Aronson started to ask if there could be other ways besides full quantum state tomography of learning quantum states. And here the idea is that instead of learning the full state, one could think of learning models in which it was only necessary to learn the essential properties of the state. And it's a very beautiful line of inquiry, and I enjoy it very much because it's at the intersection of computational learning theory and quantum mechanics. And the kinds of savings in sample complexity that we expect for these tasks are going from exponential to linear in n, where n is, again, the number of qubits. So our contribution in this paper is that many of these essential or reduced learning models are deeply connected in an information theoretic sense. So before we go into details of the specific models we'll consider, let's just talk a little bit about their general framework. So the critical observation that defines all of these models is that every quantum state defines a function from the space of two outcome measurements to real valued numbers from 0 to 1. And this function is trace of E rho, where E is a two outcome measurement, which we can imagine outputs either accept or reject on the state. And trace of E rho is the probability of E accepting on the state. So it's pretty important here that this function maps to 0, 1, which is the space of real numbers, which is our first departure from many typical classical learning models, which typically study the learnability of Boolean functions. So if every quantum state defines a function mapping to 0, 1, then a class of quantum states, for example, the set of all n-qubit states, then defines a class of functions. And classical learning theory is all about how to learn an unknown function from a class of functions. Given examples of the form x fx, where x is a point in the domain and fx is the unknown function evaluated on that point. So in quantum learning, what we're interested in is learning the function associated with a quantum state. And because we can think of the set of states as defining a set of functions, so an unknown state defines an unknown function from that set. And here, the examples take the form measurement, probability of measurement accepting. And the goal is typically to reduce the number of such examples you need. And another particularity of the quantum learning problem as compared to classical learning is that instead of having the examples be exactly E, trace E rho, we instead consider the case when we're given an approximation of trace E rho. So we're going to denote that with a tilde. And so these are two differences between quantum learning and classical learning. firstly, they map to real numbers, and secondly, the examples are noisy or imprecise. So building on this basic framework, we can then define some variations on the theme, which we're going to call learning models. And these learning models typically involve different ways of interacting of the learner interacting with the examples. We're going to introduce 4 learning models. So they are probably approximately correct or packed learning, a version of packed learning, which we're going to call private packed learning, which taps into this interesting algorithmic paradigm of differential privacy, online learning, learning by classically communicating, and shadow tomography. So the first model we're going to look at is packed learning, which was introduced by Valiant in 1984. So here, as usual, we have an unknown n-qubit row and a distribution over measurements, which we're going to call D. So these are 2 outcome measurements. Then M measurements are drawn from the distribution, and for each measurement, an approximation of trace EI rho is then computed, perhaps by actually performing the measurement and averaging them. And these measurements are fed into the learner, which is supposed to compute a hypothesis state. At test time, a new measurement is drawn from the distribution, and then the learner is supposed to output its best guess for trace e-test rho. But of course, it doesn't actually know rho, so it's going to use its hypothesis state, trace e-test sigma. And the complexity metric here is the number of training examples that are necessary. So that was M in this example, for the hypothesis sigma to be a good predictor of the value of trace e-test rho. So more formally, it's supposed to be probably, that's the 1 minus delta, approximately, that's the epsilon, correct, when in predicting the value of trace e-test rho. So we're actually also going to consider a model 1 prime, which is a modified form of packed learning that also satisfies the requirements of differential privacy. So just to give an introduction, differentially private learning is a requirement that was imposed on learning algorithms that deal with sensitive data. For instance, one could be trying to learn something on where the input data is a bunch of hospital records, but where we want to do some statistics on the patient's information, but at the same time, we also need to maintain the privacy of every patient. So although this sounds like a very pragmatic motivation, this has turned out to be a very rich vein of research in the world of algorithms. So the idea of differentially private learning is that a private learner should give similar outputs on similar inputs. So what is the meaning of similar inputs? Well, consider 2 samples, S and S prime, where each sample consists of n examples, and the samples are exactly the same except for the fact that the first example differs between the 2 samples. Okay, so what is the meaning of similar outputs? Well, the definition is slightly more technical. It means that if we feed in these 2 similar input samples, S and S prime, to a packed learner A, then each time A is going to output some hypothesis state, sigma and sigma prime. And the definition of the outputs being similar means that the distribution over possible hypothesis states is looking very similar. Now, how do we quantify the similarity of 2 distributions? Well, we consider any subset of the range, so like any ball of states, essentially. Then we're going to require that the probability that A of S outputs some hypothesis state in this subset R is at most e to the epsilon times the probability that A of S prime outputs some hypothesis state in the same subset R plus delta. The epsilon and delta are called the multiplicative and the additive parameters of differential privacy respectively. And we're supposed to think of these 2 parameters as being very small. And so the smaller they are, the stricter the requirement of similarity between the outputs of the algorithm on these 2 inputs. And so the stricter the requirement of differential privacy. So the second model we're going to consider is online learning, which was formulated by Littlestone in 1988. So again, we assume that we're given an unknown n-qubit row. And so here we can think of online learning as consisting of a couple of repeated rounds of interaction between an adversary and an online learner. So again, the online learner's goal is to maintain a hypothesis sigma about the unknown row, and the adversary is going to help the online learner. So at every round of the game, the adversary is going to provide a measurement EI, and here there's no distribution over the measurements. The adversary can choose the measurements any way they want. So the adversary provides EI, and then the online learner is supposed to respond with, I predict trace EI sigma, which is like some real number between 0 and 1. Then the adversary then responds with, you are mistaken, where mistake means that the prediction of the learner was epsilon far from the correct value, or you're correct, which means that it's not epsilon far, or epsilon near to the correct value. And in case the online learner was mistaken, the adversary then provides the actual value, trace EI row. And this whole thing repeats as many times as you want, but the complexity metric here is the number of mistakes that the online learner makes until the learner has refined her hypothesis, sigma, to the extent that no matter what new measurement the adversary gives, the learner will never make another mistake. So this is the complexity metric of online learning. So our contribution is a web of implications between quantum learning models in blue and combinatorial parameters in orange. And we can understand this web by kind of looking first at the two models. And okay, so this web is kind of bookended by the two models that we talked about. So it starts off with pure differential privacy, which is when delta is equal to 0. So that's the strictest form of differential privacy. It goes all the way to online learning. And then it's supposed to end at approximate differential privacy, which is when delta is greater than 0. Unfortunately, it actually doesn't go all the way to approximate differential privacy. And this is something I'm going to elaborate on later. We also prove a no-go theorem from this notion of stability, which classically is an algorithmic notion that's been shown to be intimately linked to differential privacy. And this last implication here basically doesn't go through. Stability basically means that a learning algorithm outputs some hypothesis state sigma within a ball of hypothesis states with high probability. So I'm going to go through each of those links one by one. So the first one that I'm going to focus on is this notion on the right, that this combinatorial parameter called sequential fat shattering dimension actually upper bounds the complexity of online learning. So what does it mean to say that this parameter upper bounds the complexity? Well, recall that I said that we measure the complexity of online learning, a class of states, by the number of mistakes that the learner has to make in order to learn the state completely. Well, it turns out that the number of mistakes is exactly this sequential fat shattering dimension. And we prove this for online learning of quantum states. So in order to do this, we had to develop an algorithm that online learns any real valued function class with at most SFAT of that class number of mistakes. So I haven't actually told you the definition of sequential fat shattering dimension because, in the interest of time, but we can imagine it, we can understand it as something similar to this notion of VC dimension in pack learning. And I guess one of the main lessons of learning theory is that learning problems are characterized by these combinatorial dimensions. The way we proved this was to actually develop an algorithm that online learns any real valued function class C with at most SFAT of C mistakes. So basically our theorem says that in big T number of rounds, our algorithm satisfies that the number of times the guess exceeds the correct answer by more than 5 epsilon is at most SFAT of C. And of course, exceeding the correct answer by more than 5 epsilon is the definition of making a mistake. So The reason we call our algorithm a robust standard optimal algorithm is that it allows the adversary to be epsilon imprecise, which actually corresponds to the fact that in real life, the adversary is typically some form of repeated measurement of the experimentalist on the quantum state, and the experimentalist can't, if the experimentalist is just going to repeatedly measure the quantum state, then the resulting estimate of the acceptance probability cannot be infinitely precise. So what is the intuition for a robust standard optimal algorithm? Well, the intuition actually comes from a related algorithm called the Halving algorithm for online learning Boolean functions. And the way it works is very simple and beautiful. So let's say that we have an unknown Boolean function over some domain, and we're again in this setting where this learner interacts with the adversary. So the idea of this algorithm is that the learner starts off with a set of candidate functions, which is all the possible functions in the class, and then at every round of interaction with the adversary, it's going to use the adversary's feedback to eliminate bad functions. So this kind of works like the game of Survivor. So at round I, the adversary gives the learner a domain point xi. And what the learner then does is that it groups the survivors into two sets, those that map to 1 at xi and those that map to 0 at xi. And the larger of these sets obviously contains at least half of the remaining functions. So the learner strategy is then to predict whichever set gets more votes, which means whichever set is bigger. So if the bigger set is the one that maps to 1, then the learner just outputs 1. And then the learner then interacts with the adversary to get the feedback, which is the actual correct value of the function. And if the prediction is wrong, then all the learner needs to do is to eliminate the set of functions that was output. Because of point number 2, which is that the larger set contains at least half of the functions. So every time the learner makes a mistake, the learner also gets to whittle down the size of the surviving set by at least half. So it's not hard to see then that the maximum number of mistakes that such a learner could make is log 2 of the size of the function class. And this can actually be improved. This is actually a pretty naive algorithm because in certain cases, the function class could have an infinite number of functions. It's possible to devise an online learning algorithm that doesn't make log 2 of infinity number of mistakes, but makes a certain parameter called the Littlestone dimension number of mistakes. So what we did was basically to extend this to the quantum case, which is a case of learning real valued functions with noisy feedback. So similar to the halving algorithm, we discretized the interval, but this time instead of the natural discretization into functions mapping to 0 and functions mapping to 1, we discretized the range into bins of width epsilon. And again, at round I, the learner gets domain point xi from the adversary. And instead of just simply counting the number of functions that map to each bin, the learner computes the sequential fat shattering dimension of the functions that map to each bin. And the learner strategy is to predict whichever bin has the largest sequential fat shattering dimension. If the learner's prediction is wrong, again, we can just then eliminate the functions in the bin that was output. So similar to the halving algorithm, the reason this robust standard optimal algorithm works is that if the learner is making a mistake, then the learner also gets to learn a lot by eliminating a lot of functions. And what actually happens is that every time the learner makes a mistake, then the S-fat dimension of the set of surviving functions actually decreases by 1. And because of this, the maximum number of mistakes is then the S-fat dimension of the original class of functions. So just zooming out a bit, let's look at a bunch of classically known relations between learning models. And these learning models are, again, the ones that we considered, but our objective, of course, is to quantize all of these relations, which means that they were proven for learning Boolean functions, but we want to check whether they hold for learning quantum states, which corresponds to learning real valued functions, but with noisy examples. So we already saw just now how we managed to devise this robust standard optimal algorithm, which characterizes the complexity of online learning quantum states by the sequential fat shattering dimension of the class of quantum states. We also quantized the relation between pure differentially packed learning quantum states and sequential fat shattering dimension of the set of quantum states. And in the process of doing so, we also came up with new bounds relating one-way quantum communication complexity to the sequential fact shattering dimension. We also investigated whether the recently proven implication that an online learner for a particular function class implies an approximate DP-packed learner for the same function class also holds in the quantum setting. It turns out that it doesn't quite. So what we managed to do was that we managed to show that an online learner for quantum states is also displays this property of stability, which means that the online learner with high probability outputs a hypothesis for the quantum state that is in some epsilon ball around some quantum state. And classically, this notion of stability has been shown to be intimately connected to differential privacy. The way of showing this was to basically force a black box online learner in which we put the RSOA to make sequential fact shattering dimension number of mistakes. And because we showed earlier that the complexity of online learning quantum states is characterized by SFAT, so being able to force RSOA to make SFAT number of mistakes implies that RSOA has completely learned the state. However, a classical technique that was used to show that this entire process can be made private, which would correspond to the last arrow here, actually is a no-go for our quantum setting. And the proof of this comes from the idea of fingerprinting codes. And the last thing we did was we also introduced what you might call a uniquely quantum learning model into this web of implications, which is the model of shadow tomography. And in shadow tomography, what happens is that you have a set of m possible measurements that you could do on a quantum state and a class of quantum states on which you want to predict the acceptance probabilities of each of these m measurements. And you're supposed to do so with using as few copies of the quantum states as possible. So we also showed that the sequential fact shattering dimension of a certain class of quantum states also characterizes the complexity of shadow tomography on that class of quantum states. So putting all this together, we get the web of implications that I displayed just now. And we also have a classical contribution because, as I explained just now, the setting of learning quantum states corresponds to learning real valued functions with noisy feedback. So the classical contribution is to show that these implications hold, that almost all these implications hold in that setting as well. And we also sped up shadow tomography on certain classes of states of interest, namely K juntas, which is when all the states come from the same K-dimensional subspace, noise corrupted states, and also Gaussian states. So with that, I conclude my presentation. So just to summarize, we've shown a host of surprising implications between reduced models of quantum learning. And notably, these implications are information theoretic in nature, which means that not all of these arrows are computationally efficient to actually implement. So what we're excited to do in the future is to study which algorithms we can now port from one model to another now that we know that these models are related. Thank you for your attention. Feel free to look up our paper on the archive. And if you have any questions, please feel free also to shoot me or my co-authors an email. Thank you.